All right, in the last video for this section, we're going to do one more example where we are deciding between using the washer and the shell method. So this time we're going to let R be the region bounded by the curves x equals 0, y equals 0, y equals pi, and x equals cosine of pi plus 2. We want to find the volume of the region formed by rotating R about the y-axis. Now, we haven't seen this region before, so we'd better spend a little bit of time setting it up. So I'm going to, let's see, I'm using the curves x equals 0 and y equals 0. And so, oops. Come on. Here we go. All right, we're using the curves x equals 0, y equals 0. Those are our coordinate axes. And we have y equals pi, which is a horizontal line up here around pi. And also this curve x equals cosine of y plus 2. Now we're probably familiar with what y equals cosine of x plus some modifications looks like. But to think about x equals cosine of y plus 2, we want to think about this maybe as a cosine function which has been reflected about the line y equals x. So it's going to look vertical rather than horizontal. And we also maybe want to try plugging in some relevant points here. So maybe we want to think about what's going on when y equals 0. So if y equals 0, cosine of 0 is 1, plus 2 is x equals 3. So y equals 0, x equals 3 lives somewhere over here. And maybe we also want to think about what's happening when y equals pi, since we know our y values are going to live between 0 and pi here. If I plug in y equals pi, I get x equals cosine of pi plus 2. Cosine of pi is minus 1, so x is going to be 1. So at y equals pi, x is 1. And I know that I'm going to be drawing half of a period of the cosine function here, and it's going to look vertical rather than horizontal, so I should end up looking with something that looks kind of like this. Not a great drawing, but a passable one. And this is the region now that we're going to be looking at, the region that's bounded by these kind of three lines here where we have this cosine line. We're going to have the horizontal line here at y equals pi and the two coordinate axes. So we've got this region here that we are going to be kind of taking the area of, and then we're revolving that about the y-axis here. So if I think about which variable I'd like to integrate with respect to here, I want to think about that sort of vertical line versus horizontal line dichotomy. And so if I'm drawing some vertical lines to start, so this would represent or correspond to integrating with respect to x, I notice I have two different upper bounds on these purple lines here. I have the upper bound corresponding to y equals pi, and I have the upper bound corresponding to this curve here, this x equals cos of y plus 2. So that tells me maybe that integrating with respect to x isn't a great idea. On the other hand, if I integrate with respect to y, I'm always using the y-axis as my lower bound, and I'm using the curve x equals cosine of y plus 2 as my upper bound. So this is also a really nice indication that integrating with respect to y is a good idea. So let's sort of say integrate with respect to y. Second, we want to think about which axis are we revolving about, and we are revolving about the y-axis here. So the hypothesis that we want to form is that since the variable of integration and the axis of revolution are the same, we want to think about the washer method here. Great. So let's go ahead and actually set up this integral. The washer method tells me integrate from the lower bound on y, which is y equals 0, to the upper bound, which is y equals pi. And we want to think about taking pi times the outer radius squared minus the inner radius squared. So the outer radius, or the larger x values here, are given by this equation, x equals cos y plus 2. And so we can say, all right, so we want to look at cos y plus 2 squared. And we want to subtract away the inner radius, but the inner radius is the line y equals 0. So we're not subtracting away anything, and we're just looking at cos y plus 2 squared dy here. And maybe we now run into something a little bit tricky, in that we have this kind of cosine sort of function to a power here, and we're not very familiar with integrating cosine functions to powers. If there were a sine floating around somewhere else in this integrand, then maybe we could do u equals cosine plus 2, and that would, and the sine of y dy would kind of take care of the du for us. But we don't have that. In fact, this is something that we're not really sure how to integrate right now. So maybe we should actually think about what the shell method is going to have us do here. So maybe we could get a more kind of tractable integral if we were to try the shell method. So let's take a look at that. So this was Washer method. It doesn't seem to be a productive approach for us. So for the shell method, what would the integral that we'd be setting up look like? Well, we would want to be integrating. This time we're integrating with respect to x. We need to break the region up into two different pieces. So we're integrating from 0 to 1. From 0 to 1, my upper bound is the line y equals pi, and the shell that I'm forming has circumference 2 pi x. It's going to have height exactly equal to, let's see, pi minus 0, so just pi dx. Well, great, this looks pretty promising so far. Let's see what the rest of the integral looks like. So we would be integrating from 1 to 3 now. We have the, again, the radius is going to be, or the circumference of a shell is going to be 2 pi x. Now we need to fill in the height. And in order to fill in the height, we want to think about what is y in terms of x. So the height is the y value on this curve. What's exactly y in terms of x? Right now we have x equals cosine of y plus 2. And so we want to solve for y in terms of x. Well, we can subtract 2 from both sides. X minus 2 equals cos y. And we can take arc cosine of both sides. So we're going to get that arc cos of x minus 2 is y. All right, great. So we have this formula here, and now we really run into a problem because we have no idea how to integrate arc cosine. We have no formulas involving the integral of arc cosine. We don't know anybody whose derivative is arc cosine. So in fact, the shell method is even less doable than the washer method here. So let's go back and kind of revisit our washer method, because this shell method is totally intractable. Great, so you go to the bottom of the page. All right, revisiting the washer method. Let's see what we can do. So maybe we want to expand out this this term here in the middle, this cosine of y plus 2 squared. So we can factor the pi out of the integral, integrate from 0 to pi. Cosine y plus 2 squared, if we FOIL it out, is going to be cosine squared of y plus 4 cosine of y plus 2 dy. Well, this, again, looks pretty good, except for this cosine squared term here. If I were just integrating 4 cos y, if I were just integrating 2, or not 2, that's 4. 2 squared is 4. Oops. So if I were integrating each of these other terms, I would be in great shape. It's this cosine squared of y that's really giving me a hard time. And in order to integrate this cosine squared, we're going to use a trick. And we're going to use one of our trig identities. And that trig identity that we want to appeal to here is that cosine squared of y is going to be equal to 1 plus cosine of 2y all divided by 2. So this is, just for our purposes, a magic formula that makes it easier to integrate cosine squared. There's a similar one for sine squared as well, though I don't have it written down, so I couldn't tell you what it is at the moment. Let's see. So let's apply this formula then. So this is pi integral from 0 to pi. Cosine squared of y is going to be 1 plus cos 2y over 2 plus 4 cos y plus 4 dy. And now all of these terms look much more reasonable to integrate. I can deal with a constant inside of the cosine function with u substitution, and for the rest of this, I can simply integrate it. So let's do one more little arithmetic simplification before we head off to actually do the integrating. So let's see. So let's break this fraction up as 1/2 plus cos 2y over 2 plus 4 cos y plus 4 dy. Now what I want to do is I want to split up the integral and integrate all of these terms separately. So I'm going to want to deal with this cosine of 2y with a u substitution, but none of the rest of them am I going to want to do that substitution. So if I integrate, so let's see, so I'll have this pi still here out front. If I integrate 1/2, I get y over 2. Great, evaluate that from 0 to pi. I have the integral still of this cos of 2y over 2, which we haven't quite talked about how to deal with yet, from 0 to pi. The integral of 4 times cosine is going to be 4 times sine. We're evaluating from 0 to pi. And the 4 integrates to 4y, so that's also evaluated from 0 to pi. All right, so I've integrated 3 of my 4 terms. There's still the question of integrating the 4th. So the 4th term here, if I let u equal to y, I get du over 2 equals dy. And so all of this is going to work out to be, let's see, so if we evaluate y over 2 from pi to 0, that's going to be pi over 2. And then if we evaluate at 0, we get nothing. So where we get 0. So we're subtracting 0, which isn't doing anything for us. If we do the u substitution in the integral here, so we're integrating from 0 equals, I guess we can convert these into u values. Let's see, so if y is 0, then u is also 0. If y is pi, then u is going to be 2 pi. We have cosine of u. We have a 1/2, which we can just kind of factor out front, and dy is equal to du over 2. Great. So let's see. So now we have 4 sine of y evaluated from 0 to pi. Sine of pi is 0, sine of 0 is 0, so this term just works out to be 0. So all we're left with is the 4y evaluated from 0 to pi. If I evaluate that at pi, I get 4 pi. If I evaluate it at 0, I get 0. All right, almost there. Let's see. So we still have this last integral to do. So this is going to be equal to pi times, we'll still have this pi over 2. Integral of, we have a 1/4 here coming from the fact that I have a pair of 2's in the denominator. So I have a 1/4. The integral of cosine of u is sine of u. And I'm evaluating from 0 to 2 pi. But wait a second, the sine of 2 pi is 0, sine of 0 is 0, so actually this middle term is just 0 here. I have pi over 2 plus 4 pi, which is going to give me a 9 pi, times pi is going to give me 9 pi squared over 2. Lovely. So we were able to use a little trick here in order to actually do this integral and compute the volume of this solid. While it seemed like the washer method was maybe going to cause us some problems at first, it turned out to be better than the shell method because we didn't have to integrate arc cosine. So again, kind of all I can say here is that a lot of these problems require you to sort of make hypotheses about which seems better. Maybe at first the better method looks bad, and so you try the other one, but then you find that the other one's impossible, and so you go back to the first. There's not really a set way of doing all of these problems. But we were able to compute the volume of this solid. Maybe if you think about what this solid is, it looks something like a vase. So hopefully this seems like a type of problem maybe that somebody would care about somewhere. So in any case, we have kind of this cool method that is going to tell us how to compute volumes, and now we're able to decide between two of these methods which one is better and which one is at the very least usable.